So, now we will demonstrate the photoelectric effect, that experiment in our laboratory. So, this is the experimental setup for photoelectric effect. So, what was the circuit diagram I showed you? The circuit diagram just so always for when we are going to do experiment, we should have circuit diagram in our hand, and then we should connect this all component accordingly. So, here, so this let us see which one is photocell. In this setup, which one is photocell? This is photocell basically. So, it's a photocell is basically inside. Okay. So, inside this element is there. So, this the cathode is written K, right. This the cathode and this the anode. Okay. So, it is inside the box. We cannot see now. So, now light will fall on this cathode, right. So, light will fall on this cathode. So, light will fall through this is the entrance of light. So, this is the entrance of light. Okay. Here we have put a filter basically, as I mentioned. I have to, yes. So, this filter, so this the entrance of light. So, we can, so inside there is a photocell, cathode and anode. Okay. So, this just we just, because all the time we do not put this light on the photocell. So, its sensitivity will decrease. So, that is why we just closed it. Okay. And then we just move it to, oh, okay. So, I think this way, yeah, you can close it, you can open it. Okay. So, light, this mercury light from this source is coming out from this source, light is coming out, mercury source, it has different wavelength. Okay. So, this will put this way. So, light will fall on this photocell through this entrance. So, actually we want monochromatic light to fall on this photocell. So, we will use this, these are basically interference filter. So, it will only allow light of wavelength 405 nanometer, 405 nanometer. Okay. So, that is the wavelength of light will pass through this filter and other light will be stopped. So, so interference phenomena is used for this filter. So, such type of filter we have 5 filters. Okay. So, we have 5 filters. This is the another filter which is having 366 nanometer, 366 nanometers, and then I have 3 more. This is 436 nanometer, 546 nanometer. So, it is you see this is looks yellow color, you know 546, it is the 500, you know this sodium D lines, this wavelength is 500, 580, 589, 589, I think 589, around 590, 590 is the wavelength of sodium D lines. So, that is the yellow color. So, it looks yellowish, this bluish wavelength is lower, is bluish, this yes towards I think it is a green. Okay. So, filter itself, because only that type of light is passing through it. So, that is why we are basically we are seeing that color of the corresponding wavelength. So, and then I have another one going towards orange, going towards orange, that means higher wavelength. So, here you can see 578 nanometer, 578 nanometer. So, it's also we can tell yellowish, going towards red, orange. Okay. So, we have basically 5 filter, interference filters for selecting monochromatic light. So, I think I will start with the lowest wavelength. It is a 366 lowest wavelength, higher um, frequency. So, this I will now put in front of the cell. I will put in front of the cell. Yes. Okay. So, now I will turn it towards the light source. Okay. So, now light is falling on this filter, but this it is not entering into the it is not entering into the cell, because its entrance is closed. As I told, this I have kept it in closed position. So, in this condition, now what we will do? So, light will fall on the cathode and then electron will emit, and that electron will fall on the anode, and corresponding anode current will get. So, let us see this circuit. So, now you see from here, basically this from inside, you see this type of. So, these two end are coming here, these two end are coming here. Okay. So, from here, so this two end, one is going towards the nano ammeter. So, one is going towards the nano ammeter. So, this is the nano ammeter, this is the nano ammeter. Okay. And from nano ammeter other end, nano ammeter, here this two end, one end is there connected here, and another end is going towards the voltmeter, another end is going towards the, see, another end is going towards the voltmeter. Okay. And so, one is going towards the voltmeter and other part is going to the rheostat, other part is going to the, so rheostat. Okay. Rheostat. So, this is the rheostat. So, other part connection here rheostat. So, this connection and this connection is I showed you. Now, this anode, this part, so one will go to the voltmeter. Okay. So, anode other side is this one will go to the voltmeter and rheostat. So, this one is going to, yes, this one is going to the DC power supply. Yes, it has come to the DC power supply, and also from DC power supply or the rheostat, other whatever, this should come to the voltmeter. So, I can see, yes. So, this is coming from the other end, this is coming to voltmeter, this is coming to voltmeter. Okay. So, one is from here, another is from here. Okay. So, these two connections, so you have to check it. Okay. So, and rheostat other end, of course, with the one is connected here and another must be connected to the DC power supply, whatever this one, it is there. Okay. It is connected with this power supply, other end of the rheostat. So, this the circuit diagram whatever we have done. So, exactly this circuit diagram is made here. So, always we should draw the circuit diagram before doing experiment, and we should check the connection whatever we have made, whether that is as per our drawing. Okay. Now, we will do experiment as I described. So, what the data I have to take, yeah, experimental data recording, least count of voltmeter. So, find out the least count of voltmeter. Here is you can see this 0.00, okay. So, it is the volt, and this after decimal 2, that means it is 10 millivolt is the 10 millivolt is the least count of this power supply. Oh, sorry, it's the voltmeter, not that one, not that one. It's here. So voltmeter basically. Yes. So we have chosen the scale 2 volt. Okay. So you can get change after decimal point 3. That means 1 millivolt. 1 millivolt is the, or 0.001 volt is the least count for voltmeter, that we should note down. Then what is the least count of the ammeter, nanoammeter? Of course, it is, we have taken 100 nanoampere. So, it is showing 35 nanoampere point. So, 0.1 nanoampere is the least count. So, 0.1. So, 0.1 nanoampere is the least count, that we should note down. Okay. So, yes. So, which scale you are choosing, that you have to see, here 100 nanoampere, that scale we have chosen, and here reading showing 35 points is a varying anyway. So, it should, because some fluctuation of light and this something is happening, and separation between lamp and filter at front of the photocell. Okay, separation between lamp, this is the lamp and the filter. So, this distance generally we note down, because that we should not change this distance during the experiment. So, we just take a scale and measure it. Okay. This is the filter and this is the phase, of just measure, and you can note down that one. Okay. So, now we have to determine the stopping potential. So, we will choose particular wavelength, say lambda equal to, now what is the lambda I have chosen, this 366, probably 66 nanometers. Okay. So, I will note down, and corresponding frequency I will calculate. This is the c is the velocity of light, 3 into 10 to the power 8, 3 into 10 to the power 8, 8 meter per second. Okay. So, for that, now what I will do, I have to change the voltage. This is the reading of voltmeter, and ammeter, nanoammeter we have to take. Okay. So, just I am showing, I am not knowing this. So, here the rheostat I have kept at, you see. So, between these two, this whatever the resistance is included. So, I have kept at 0 resistance. So, here that is why it is showing this voltage is 0. So, there is a minor fluctuation. Okay. This voltage is 0, right. So, no. So, this voltage is 0, it is not because of that there is no voltage applied to the anode, it is not because of that. Okay. We should get maximum current at this 0 voltage, because we will apply negative voltage. So, here it is 0 because this shutter is closed. Now, I will open the shutter, Oh, I have to give other side. I have opened the shutter, but why voltage? Okay, voltage is 0, that is true. Voltage I have applied 0, so I confused with the voltmeters and ammeter, nano ammeter. So you have to look here, okay. So voltage is 0 because I have kept it as resistance 0. So no voltage is applied to the anode, okay. Now this time current you are getting, that is 80, yeah, 88.4 or 89, you note down that one, you note down. So 0 voltage, I have applied 0 bias and this current is 88, okay, nano ampere. So basically, if I showed you the circuit, how this cathode and anode, the photocell are connected with the nanovoltmeter, nano ammeter, this voltmeter, this is the voltmeter, okay. So this voltmeter will give reading the voltage applied across the anode or between the cathode and anode, okay. So it's a negative voltage will be applied, so connection is made in that way. So this is the constant power supply, DC power supply at 2 volt, and this is the rheostat. So now rheostat position, now here this it is showing 0 voltage, okay. So 0 voltage is given to the anode and corresponding photocurrent earlier. So there was some problem in the circuit, loose circuit, so I have corrected it. So actually it will be not 88, so it is reading is 0.5, okay, 0.5. Now I will change the, I have to change the this voltage. It's I am changing the rheostat resistance. So you see I am increasing the resistance, that means voltage drop will increase, okay. But again I am, so it's a current is decreasing, but somehow this fellow is not giving me, this fellow is not giving me reading. So somewhere some, I think loose point is here, okay, okay. So okay, now okay, now it is giving reading. So it should be 0 at this position, it should be more or less 0 at this position. It's digital one, it always fluctuate, okay. So it's 0, right. So you have to give time to settle it down. So it's more or less 0. Now this current 105, now I am seeing just change, applying voltage, bias voltage, you see it's changing, it will change the voltage, that. So I have to take this reading, I have to wait, and actually one should take, so this and note down this current. So I have to make this current 0 and corresponding that voltage I have to find out. So I am changing and just looking at the current decreasing, increasing bias voltage, current decreasing. So I should note down, I should note down, I should note down, but I am not noting down, just I will continue and just only I will note down the stopping voltage. So current is decreasing, current is decreasing, voltage is increasing. So at which voltage current will be 0, that I have to find out, okay, that I have to find out. So I have gone slightly more. I should. It's slightly hard. Okay, so it's more or less current is 0. Yes, it's more or less current is there is a fluctuation. So this the uh, it's uh, it's 700. We can take this 700 as the stopping potential. It's the varying. So I will note down this for this corresponding wavelength. The stopping voltage is say 700 millivolt, because this is a 0.700. So it's a millivolt. Okay. So but here I have written volt, so I should write 0.700 volt, and corresponding current is, this is for this, and corresponding current is 0. Okay. So for different filters we should just do the experiment. So I will do the experiment for next filter, and we will put at the same place, because intensity will keep constant. Okay. So I will change this filter. I will change this filter. I will go for the next one. So 405 nanometer, 405 nanometer. I think I will go to the extreme one. In between I will not do. Okay. So that is the, I think 578 nanometer, 578 nanometer. So in this case current should be drastically fall at 0 bias voltage compared to these other filters, and stopping voltage will be very small for this in principle. Let us see, because higher wavelength I will keep at the same distance. Okay. So we will expect that brightness will be, intensity of light will be same. Okay. So I have to actually I have to keep it all the time starting from 0, starting from 0. So here you see this, I am not getting, you see, even at 0 voltage, even at 0 voltage I am not getting current. Okay. I am not getting current. So we are getting 105 nanoampere for the, for that filters, for that filters for 405, or not 405, 36. So this is the highest wavelength. So this is the highest wavelength, 366 nanometer. So energy is highest. We are getting 105 nanometers. You see, when we are using this higher wavelength, that means lower frequency. So this h nu, here h nu corresponding this wavelength, okay, corresponding this frequency. So that is not, that is even less than the this, that's EV, not EV. What I should tell this, h nu, what about this energy of these photons? That energy is less than the work function. So no electrons are emitted. So that's why this is happening. But let me check using this one whether my setup is working well, or any, due to any problem that current is not showing. So this I am using 405 nanometer. Okay. So earlier it was 600 something, 578, now it's so I should get current, I should get current, I should get current. Yes, I am getting current. It's you see 18, it's around 18 17, 18 nanoampere. So, now here wavelength is higher than the 366 nanometer. So, for 366 nanometer 105 we are getting, whereas for this we are getting 18. Okay. So, we will increase the wavelength and we are getting the current, lower current. That means ejection of the electron, although intensity are same, because that distance after, although light intensity are same, but different wavelength, because of the different wavelength. Okay. So, ejection of the electron from the metal surface are different. So, that is why plate current are different, even we have not applied any negative bias at 0 voltage. Okay. So, this current is decreasing. So, that is what. So, for all things one has to note down and find out the stopping potential. For this also one has to find out the stopping potential. Okay. I have to make it 0. So, it is a decreasing, that voltage is increasing. Yes. So, one has to do properly. So, it is more or less 0 current, and for that corresponding stopping voltage is 0.412. So, you should note down what is the wavelength. So, this next wavelength is 405 nanometer, and stopping voltage is 0.413, okay, for 0 current. Okay. So, we will note down this for all filter, we will note down and get the stopping voltage versus this wavelength or corresponding frequency. We will plot the graph V versus nu, and from there we have to find out how to find out slope. You must be knowing. Okay. So, this experiment is done, and this I will not just I will show you that how to do this one, dependence of photocurrent on the intensity of light. So, intensity of light, so for a particular light here 405 we have used. Okay. So, let me put it at 0 bias. Okay. Now, if I change the from the source, if I change the distance of the filter, so keep at higher distance. Okay. Okay, here current also, I think for this doing this experiment it is better to take this. So, it will better to take this higher, lower wavelength, higher, yeah, this one 366. So, it was 105. See, depends on distance, 105. So, you see for this now intensity I am just changing the distance, and I am getting the variation of the current, because intensity of light is decreasing falling on the photocell, because the distance from the source to the photocell are changing. So, if I increase this way, okay, you are getting, yeah, is increasing. Okay. So, for a particular distance here, for a particular distance, now what is the stopping potential for that one? If we want to find out, let us find out. To make it 0, So, to make it 0, uh, so if you change, so one has to, it's become hot and then changes, you know. So, earlier for 366 nanometer stopping potential, we noted down this 700, around 700 millivolt, and for now it is coming around 800 millivolt anyway, but this is for 366. If I increase the bright intensity, so the stopping potential whatever I, so this stopping potential should not change much to make it 0. So it's the 100. So earlier I kept at 105 the reading, the distance I kept at 105. Yeah, around this point I can keep 105, and this voltage applied 0. Now what is the value I am getting for stopping voltage? Just let me check it to make it 0. Okay, it's around 900. Okay, it's around 900. Now keeping that, to make it 0, it's around 1 volt, around 1 volt, but it's a sensitive one. One has to around 900. Okay, around slightly more than 900. Anyway, it's fluctuating. Now if I change the distance, what happened? Intensity, incident intensity I am changing, you see. I change it. So okay, so to make it 0, how much I have to change? So it's around 700. Okay, so for that distance the stopping voltage is 700. So for different distance you can find out the stopping voltage, starting from this, of course, here, starting from this, of course, here. Okay. So at that distance, so at 0 voltage, so this is the 33, and now for the stopping voltage what will be the, so at different distance. So this will basically, we will note down, as I told, the separation between the lamp and filter you are varying. So you are noting down the photo current for 0 voltage, and then voltage you are changing and getting the stopping voltage. So for different distance means intensity for different intensity for the same wavelength. So, uh, how the photocurrent are changing. So, that is what one can see from this data. So, just I showed you how to do it, and this if longer time this light falls on this photocell, it's basically current fluctuate. So, we should quickly take data, or when you are not taking, so you have to close it, so that unnecessary light will not fall on the photocell. So, that is the precaution one should take. I think this is the experiment for yes, it is a for photoelectric effect. So, clearly we are able to demonstrate that the frequency, the current we are getting plate current or anode current. So, that depends on the frequency of the light. It does not, it is very sensitive to the uh, frequency of light, because when we use this higher wavelength, then we saw there is no current. Okay. And when we are using lower wavelength, we are getting higher current, and wavelength are increasing, current is decreasing. Okay. And also intensity, that current is decreased with the distance, with the intensity. So, there is a number of photons basically. So, if number of photons increased on the cathode, so then what will happen? Uh, if the energy of that h nu is higher than the threshold work function, so we will get current will increase. Okay. So, intensity is increasing, current will increase. But if for red light, whatever I showed you, for red light, this wavelength is 578, for that one I showed you that for that, so we are not getting, we are getting zero current, Okay. So, even putting at zero bias means there is no, so stopping voltage, there is no question of stopping voltage, even without negative voltage to the anode, we are getting zero current. And if you change the distance, nothing will happen. If you increase the intensity, also does not matter. So, there will not be not any current in the nanometer, we will see nanometer, because there will not any ejection of the electron from the metal, from the cathode surface. Okay. So, since it is nano ammeter, so it's they are very sensitive. Okay. So, we have to take reading, that there will be fluctuation, we have to try to take reading that it is fluctuating from plus minus something. So, average reading we should take, and I think this experiment, if you find out the slope and you can calculate the h Planck's constant, and this very give very good accurate result uh, from this measurement. So, I think I will stop here. Thank you for your attention.